So first, let's go. Yeah. So hydrogen, then helium. You understand the s orbitals, p orbitals? Okay. So we'll go back to that then. S. So S, and you have S and P, and S, P, and D. So this is how, so on this side is the s orbitals, and this side is going to be the p orbital electrons.
This side meaning.
So everything in this chunk right here.
Okay. What about this purple strip?
This purple strip is also going to be in the p orbital, or usually. So the only exception is going to be this helium here.
Okay.
Because what happens is you have...
Love you, my baby. God bless you.
Love you too. Thank you. So you have... Your shells look like this as you kind of fill in. So you have your orbital for S, it only has one block.
Okay.
So S only has one suborbital. So S, this one's going to have 2 electrons in it, one spinning down and one spinning up.
Okay.
So each level is going to have an s orbital. Starting from the first period, period 1, it's only s.
Okay.
So hydrogen has 1, then the helium on the other side has 2.
Why does
Helium, because each, so hydrogen has how many protons?
Can I look at the periodic table?
Yeah, well, of course. So I can pull it back up. Hydrogen, looking at its atomic number 1, it's just 1 proton.
Yep.
Helium, 2 protons, so therefore it's going to have 2 electrons. A neutral atom or a neutral element is going to have the matching an equal number of electrons to protons.
Okay. Yeah. Makes sense.
So obviously, so let's also consider, let's just stick with this. So hydrogen, helium. So now this s orbital is full. So now we have to move to the next one. So this is going to be S2. Or, I think it's, yeah, so this would be the 2s orbital. So 2s. So this one's now going to have 1 spin. And that's going to be our lithium. So that's lithium. Then beryllium. And this also has, so lithium is also going to have this full s1 orbital. So hydrogen.
How would we determine that? Sorry.
So hydrogen has 1 electron. So it's just going to have that 1 electron. Helium is going to have 2 electrons. So it fills the entire s1 orbital.
Okay.
So s2 orbital, it's going to have 1 s2. So that's going to have both of these. So that's 1, 2. And then now it's going to also have this next s orbital. So that's 2s1. So this 1 meaning we only have 1 electron here. So that makes 1, 2, 3 electrons.
Wait, so show me that again. What means it's only one electron?
So it only, so lithium is element number 3. Meaning it has 3 protons. For it to be balanced or neutral, it also needs, yeah. So we've already filled this shell. So we can't fit any more in here. So that's when we move to the next one. we only need one in here. So that's where we only put this one spin in here.
Good night.
Night.
Only need one. What was it again?
So we have these two, then we have an additional shell. We have, the next shell is going to be the 2s orbital shell.
Okay.
So that's where only one electron here is needed. When we go to beryllium, I believe it's beryllium. Yeah, beryllium. It's going to be 4 protons.
Are you just naming the different elements as examples?
Yeah, I'm just going to go one by one to kind of show how they build.
Okay.
So needs 4 electrons
To be neutral.
to be neutral, correct? Because you're going to have ions, and those are not going to have a neutral charge. They'll either have an extra electron,
Okay.
because electrons are negative charge. An extra electron makes it a negative anion.
Yeah.
And then if it's positive, it means it's missing an electron, meaning that the positive charge from the protons make it a cation. So for this we have 1s, so we can put 2 in here. So we go 1, 2, that's filled. The next one is 2s, so we can put 2 in here. So we go 1 and 2. So that's beryllium. Oop. No, not that one.
Oh, and so is the one pointing up supposed to represent a cat or an one pointing up supposed to represent a proton and one pointing down supposed to represent an electron?
So no. So each of these, everything in this is going to be an electron.
Okay.
Electrons do not like to be around each other.
Okay.
So
They're separated.
if you have this orbital, this electron, let's say it's going around this way.
Yeah.
If you also have another electron that's following around it this way, that means they're always going to be right next to each other.
Okay.
This is a very crude way and not super accurate because of the way quantum physics works.
Okay.
But this electron would rather go in a different direction.
Gotcha.
So that's what the up and down arrows is. One electron goes one direction, the other electron goes the other direction. That's what. That's how it squeezes in 2 electrons into one shell.
Gotcha.
So we put in 1 here. That's 2 electrons. This shell is full. So now we move into the 2s. We can put 2 in there. This is full. So that's beryllium. And then kind of the next one, we have an additional shell within, or we have an additional subshell. So we have our additional orbital in this shell. So let me clarify that.
Okay.
So 1s, then we have 2s, then 2p. So this is shell 1, shell 2. Each shell has an orbital. So s orbital. The first one only has the s orbital.
Okay.
The second shell, we have the s orbital, then we add the p orbital.
Okay.
And then shell 3, we have an s orbital. So this would be period 3. You have the s orbital. Then I want to make sure I'm getting this right. 'Cause if I recall, I'm going to pull up. Let's do. Diagram. So let me see if I can find. Here we go. So the first shell, we have the s orbital. Once that gets filled, the next period we have to start filling this one. Once this 2s orbital is filled, in the same shell, we start filling the 2p orbital.
Okay.
So each orbital, and this is where it kind of gets a little bit more complicated with the orbital geometries, because the s shells are like this, just a circle or a sphere. I'm just going to do it like this. Put an s there. Then the p orbitals, let's say this is the nucleus. It's going to have an orbital that looks probably more like this. And this is going to go in, let's see. So 1. So yeah, this would be, let me make sure I'm drawing it right. So that's P or tall diaphragm. Because it's a different shape, it makes it easier to squeeze more into this next shell.
Gotcha.
So this p orbital is going to have 3 different components. It's going to have the x, the y, then in 3D, you're also going to have a z component. So think of these as being opposite sides of a dice.
Okay.
So in this case, we have your spins going kind of like one here, and then one here. You can imagine it kind of that way. So your S1, then your 1S, where you can fit up to 2. Then your 2S, where you can fit up to 2. S orbitals will always only fit 2. So one box. Then p orbitals actually have 3 parts. Think of this as these 2 sides of the dice, these 2 sides of the dice, and then these 2 sides of the dice. Because the dice has 6 sides.
Yeah.
So each of these, 1, 2, 3, 4, 5, and 6. So you can fit 6 electrons into a p orbital. And it's going to have 1, 2, 3 suborbitals.
Okay. And then how would I distribute it if it had all those layers? How would I know how to distribute?
So
Write it out.
So let's say, let me see a good element I can choose. Sulfur. I think sulfur is going to be, actually, I'll go oxygens. So I don't have to write as many. So, s orbital, then 1, 2, 3, 4 in the 2p orbital. So the electron configuration is going to look like this for oxygen. So you're going to have your 1s. It's going to have both 1 and 2. That's filled. That's 2 electrons. And we need a total of, oxygen is 8, so we need 8 electrons.
Okay.
So 2s, we're going to have, yeah, so that's 2, we go 3 and 4, so that's that one filled. Then 2p, we're going to have 1, 2, 3. Remember, think of each of these boxes as one of the orbitals.
Okay.
So if we got 2p, it's going to want to go 1, then it's going to move to the next one, 2, because electrons really, really do not want to be near each other.
Okay.
So instead of filling 1 and 2 like this, it's going to fill the next suborbital.
But still going downward.
Yes, so it's going to fill in one direction and then fill in the next direction. So it's going to go 2p. So we got 1, 2, 3, 4, 5, 6, then 7. Then we just need one more electron, 8.
Okay, and
So
go
this-
back to the beginning.
So yeah, so this is for an oxygen. So we got 1, 2, 3, 4, 5, 6, 7, 8. So yeah, this is all the electrons you need, and they're which orbitals they naturally will fall in.
Okay.
Because let's pretend for a second you have a lot of oxygen and you make it super hot. It's just oxygen, so you're not going to have any combustion or chemical reaction. The next one's going to be 3s orbital. And for oxygen, it's not going to have anything there. It's going to be 3p. Then 3d is actually down here. It's going to show up in the d period. Just a wild guess. How many squares do you think it's going to have? Or suborbitals?
For 3p?
Or for 3d, the d orbital. So this is...
6.
So we have 1, then we go 1, 3. It's going to be 1, 3, wild guess.
4?
It's going to be 5. So it's just going to be 1, 3, 5, 7, 9, and so on. So it's going to be odd numbers of
Gotcha, okay.
suborbitals. So 3D has 5 suborbitals. So how many electrons will fit in a d orbital?
Based on the ones we have.
So it's always going to be two electrons per suborbital.
Okay.
So if we have 5 suborbitals,
10.
it's going to be 10 electrons.
Okay.
So as you kind of fill, so let's say, let's go take a look. So let's go to something like argon. Actually, yeah, argon should be good. So that's element 18. And then again, this is everything in this area right here is going to be your s shell or your s orbital. Everything in this section is going to be your p orbital. This is going to be your d orbital.
Okay.
And d is really weird because when you're in your 4th period, this is actually the 3d orbital. So after P, it decreases. You go to D. This is going to be D3 instead of D4. And this is your F orbitals. This is why you have this chunk here, because these technically go in here. But because they're their own orbital, it's kind of hard to diagram it that way. So these would be in your F orbital. And again, they start at 6, but it's actually going to be 2 less than that. So this is going to be D5 orbital. This is going to be the F4 orbital, even though it's inserted in 6. So after the first 2, it gets 1 less than the period, an additional 1 less than the period.
Okay, so could you write out an example?
So let me
One
see.
being 1 less. Yeah.
So let me do, so let's say, I'm going to choose argon, 18. So it's 18. So we know we're going to have 1s, we're going to have both of those, that's 2, 2s. That's me another 2, that gets us to 4, opposite directions. 2s2, and 2p, we have 1, 2, 3 suborbitals, so it's 2, 4, 5, 6, 7, 8, 9, 10 electrons. So that's that full shell. And then it's going to be 3 S, that's me 11 and 12, so that's 2. And 3p is going to be so 10, 12, 13, 14, 15, 16, 17, 18. So we can say this is me 2p6 because we have 1, 2, 3, 4, 5, 6 within this p orbital. This 1, 2, 3, 4, 5, 6, all 6 in there. So that's me 6 in the 3p orbital. So it'd be written as 1s2, then 2s2, then 2p, and p orbitals have 6 electrons total, or possible.
Yeah.
3s, and 2 electrons in there. This one is me 3p, and then all 6 electrons in there.
Okay.
So going back to, let me find.
Can I pause you real quick? And then for
Yeah.
what element is that as an example for what would that?
So this is for 18 electrons, so that'd be for a neutral argon.
Neutral argon, okay.
Yeah. So let's go just one backwards. A neutral chlorine is going to have 17 electrons. So I can just,
And again, I'm so sorry. And how would I determine? So it's just the placement on the periodic table for determining how many orbitals or what orbitals there are.
yeah, so basically the periodic table, whoever designed it, because I don't know off the top of my head, they designed it nice and neatly to show different groups. For example, these will all, the thing about elements is if they are able to, or if they are able to react, let's say sodium, it wants, its most stable state is going to have a full, this full p orbital.
Okay.
To get to this full p orbital, it would have to lose 1 electron, making it positive. So it'd shift down to, it would lose the entire third shell, and it's going to have the same electron configuration as neon.
Okay.
But it's only because it is an ionic element, because it's going to be missing an electron. So this would be for argon. But this is also the same as, let me go back here. Argon. Let's go potassium. K plus. Because if you add 1 electron to potassium, which would be, potassium would be 1s2, then 2s2, 2p6, and 3s2, and 3p6. And the next one's going to be 4s1. So once we get to this one, if we knock off 1 electron, that's just going to be this 1 electron. So that's going to go to 0. There's no point in writing this at all, so we can just delete that. This is now exactly the same as an argon,
Okay.
as far as the electrons.
Is it like adding a negative, essentially?
Yeah, so again, kind of, this is where it gets annoying with electrons being negative charge,
Yeah.
because when you say minus an electron, it becomes positive. It becomes a positive charge.
Makes sense.
Because if you have, let's see, 16, positive 16 because they're protons, then negative 16 because they're electrons, just sum them up, you get 0. 0 means no charge. No charge means it's neutral. Now, what if we have 16 protons? And remember, protons determine the species of the element, so it doesn't matter. I can have 0 electrons here. element number 16 is sulfur. So no matter what, as long as there's 16 protons here, it's still sulfur.
Okay.
But plus electrons are negative. Let's say I add 2 electrons. So instead, I'm going to have,
16 plus 2?
so I'm going to have 18 electrons.
Oh.
So I'm just making it negative because the only reason this is here because it's a negative charge. Because electrons are negative.
Yeah.
So what's that going to equal? The 16 positive, then 18 negative.
Negative 2.
That's your charge. Your charge is negative 2. Even though we have added 2 electrons,
Yeah.
you're going to get a negative charge.
Okay.
So just keep... So again, adding electrons is going to be additional negative charge. So you have your positive, that's your protons. Then you're going to have negative the number of electrons. So this is a good way to determine what your total charge is going to be. So you can have 2 elements with the only way to have 2 elements that have the same electron configuration is if one of them is ionic. One of them is going to have either an additional electron, because let's go look at this one. So the only way for a chlorine to have the same electron configuration as argon is if you had one additional electron.
Okay.
You can even have a silicon can be the same as an argon. Electron configuration. You'd have to have 1, 2, 3, 4 additional electrons to make that happen.
Okay, but wouldn't it make the charge negative? How would that affect it?
Absolutely. Because if you have 1, 2, 3, 4 electrons, it would be a negative 4. So it'd be S negative 4 electron config equals argon electron config. Make sense so far?
More or less, yes.
Okay.
And then if whenever you're done with the video, could you please just email it to me?
Yeah. So S P that's me 3. Then S P and D. D's gonna be I'll squish there, but it's gonna be.
Why are there multiple S's again?
So this is your first shell.
Okay.
This is your second shell. This is your third shell. So once you fill up your first S shell, then you can move on to the next S shell.
And is it like a row S and P, S, S
Yep.
and P, S, P, D?
So then you're going to go, once this one is filled, you can go to the next p orbital. Once that's filled, you can go to the next shell. That's going to be the S, then P, then 4S,
And then there could be a maximum of
4P
2 electrons per each.
per each suborbital, yes. And this is where, if we look at it, that's 5, 3 suborbitals, 3, 1 suborbital, 1 suborbital, 5 suborbitals, 5 suborbitals. So this one's going to go the 3p, 3p, so 3p, then it's going to go to the 4s. And this is where when we go to the next one, we're going back from the 4s to the 3d. And then when we go from the 3d, once that one is filled, we fill the 4p orbital.
Okay.
So this is where,
But would you do the S in that next row first?
let me see. Let me see if I can find it. Yes. So yeah, you fill an entire orbital before you move to the next orbital.
Okay.
Then once you fill, you follow this. Oh, this. You follow this order. So this is kind of following the diagonal lines.
Gotcha.
And this is kind of something that's I just memorized by this way. Because 2s, once the 2s is filled, you just fill the 2p. Once 2p is filled, you can start the next one. It's be 3s, then 3p, then 4s.
Yeah.
Then you kind of step back to the d.
Okay.
Then you go back forward and start working your way back through each of the orbitals, each of the orbitals in that direction. Again, you fill each orbital before you move on to the next orbital.
All right.
So that's how your shells get filled.
Okay. So could you just real quick